Okay, let's see if we can address the question of what are some practical implications of the diffracting plane having to be perpendicular to the surface, or sorry, parallel to the surface. So in a typical experiment, we have a powder, and we have, with that, each separate crystal has a random orientation within this structure. And so our expectation is that we're going to see all the diffracting planes and have a very specific intensity, relative intensity, amongst those diffracting planes. Something that we partially addressed with the structure factor. However, if we don't have a very nice powder, there can be some practical limitations to this. So let's take a look at a couple examples of this. So here on the left, I've got a sample of brass, and it's been rolled, and you can, so this is basically the microstructure, and it's been rolled along this direction that my mouse is moving. So the grains tend to be aligned with that direction. So you can see all these elongated grains, right? So specific crystallographic directions will be sort of aligned with this direction. So this isn't like the powder sample, because these are no longer random. This sample now has a preferred orientation. So if I put this sample in an X-ray diffractometer, there's no longer going to be these random crystals. There's going to be highly aligned crystals in one direction. And so the relative intensities of the diffracting peaks that I would expect for brass are going to be different, because I have a very predetermined arrangement of those grains. So this is something we call preferred orientation or texturing. So this can affect the relative intensities of X-ray diffraction peaks, sometimes completely excluding certain peaks. So that's the example of a rolled sample. The same thing can actually happen with a powder or a sample that does contain discrete particles. So this is an example. So we have single crystals. Each one of these pieces is a single crystal. However, this is a single crystal of a metal that's shaped into a very specific rod-like shape. And those grow in a very specific direction relative to the crystallographic direction. So the flat regions here tend to always be a specific crystallographic plane, just like the other faces would be a specific crystallographic plane. So as you might imagine, if you lie these on a substrate, like our holder back here, they tend to lie with the flat side down. And so this is, again, another example of we have a very preferred orientation. And so some crystallographic planes are going to have a much higher intensity than we would expect if we have a random mix of our particles and random orientations. So this is, very very preferred orientation of these sort of rod-like nanoparticles. So the same thing can happen in both of these types of samples. And so real materials, if they are a bulk sample that may have some texturing or preferred orientation, or if you have very specific types of growth in certain crystallographic directions, we can have this preferred orientation. And so that's going to affect what samples that we see. Because of this preferred orientation or texturing, ideally for this powder X-ray diffraction, we don't want samples like this for an ideal scenario, unless we want to sort of study what's going on here with the texturing or orientation. Instead, we prefer what's kind of shown here, is we want a large number of crystals, and you want them to be very small, And you want them to be randomly orientated so that we get the ideal mix of relative intensities from sample to sample. The larger these crystals are, the less random it becomes, and the more likely we're going to have something like this, where there's only the diffracting planes that are parallel to the surface, right? So that's always going to limit what we see in those cases. Okay, another limitation that we need to address when we're looking at real specimens is the fact that our x-rays only penetrate a certain depth. So this would be important if we're looking at structures where the surface may be different than the interior. And so we need to look at the depth that x-rays penetrate to see if we're sampling enough material. And so here's a table from your textbook 2.3 that gives us some of these depths for copper K alpha radiation at different incident angles. So we've got a couple ceramics here, molybdenum oxide, calcium carbonate, and the medicine aspirin. And so that kind of gives you a range of different densities for these materials. And sorry, the densities are listed here. And then at different angles, you see the penetration depth. So in all these materials, the more dense something is, the less the X-rays will penetrate. That's fairly self-explanatory. But also the penetration depth goes up with increasing angle. So if you go from 20 to 40 to 60, you see that the depth goes from about 2 up to 4. So it doesn't change all that much. But down here for aspirin, it goes from 82 up to 161. And this is in microns. So, you know, so we have a range of anywhere from 1 micron up to hundreds of microns for the depth. So that's typically a fair distance, but if there are some surface structures that are different than the interior on the micron scale, then this could be an issue for your X-ray diffraction experiment. So that's something to consider in terms of the penetration depth. So a good rule of thumb that we can have for the penetration depth, specifically if we're talking about metals and alloys, is that the penetration depth is on the order of several micrometers or microns. So that's just a kind of a good rule of thumb to have. So that's kind of equivalent to this oxide that we have here.